Good evening, everyone. My name is Jyoti Sharma, and welcome for the week 6. And the live session will be from 6 to 8. Uh, I yeah, this is brief introduction. You already know that right now I'm a PhD student from ISO Bhopal, and I already have taken some NPTEL courses. So I think that will help me to teach you in a nicer way. And yeah, I have a lot of MCQ question, and we will try to solve it with the discussion. And your participation is highly valued. We already have talked about week one. In week one, we started with a very basic thing: what is the environment, what are different compartment we have, how different compartment have different characteristics, and why we need to know about different characteristics of each of this environment compartment, what will be the impact on the receptor, for example, for human beings. So this we tried to cover in week one. Then week two, we started with the partition constant because it was important. For example, there is a pollutant one or A. So where this pollutant A will go, either it will go to the water or to the air or to the soil, or you can say where you will find the exposure for that contaminant, right? So it was important for us to understand what do you mean by this partition constant. We learned about the partition constant for soil air, soil water, air water, like this. So we already have talked about this at length. Then we started with the week 3, and in week 3 we started with some sampling and standard, then detection limit, why it is important for us to maintain the standard whenever you are creating some policies. And also it is very important for you to maintain the accuracy, the precision whenever you are monitoring or sampling, sampling for any of the contaminant, right? So we learned these things in week 3. Then we moved to week 4, and we started with how we can if there is some organic contaminant or pollutant in the water, then how we can extract it out. And this extraction is nothing but based on partition coefficient that we learned in week 2. So we learned about these things in week 4. Then last week was our week 5. We started with some analysis method. Then we talked about how if we do have any solvent, then and we need to concentrate it, right? So for example, if we have some contaminant A, and that contaminant A we have stored into some liquid, right? But we need to concentrate it. So how we will concentrate? We tried to explore some of the methods uh, to concentrate, to extract it, right? So we learned it in week 5. We are yet to learn about this chromatography and mass spectrometry. So I have few question, 10 to 15 question I think I have on the on this chromatography and mass spectrometry, and then we will move to week 6 content, right? So right now we will explore these two things. And I again encourage you people to please do participate. Please don't be hesitate giving the answer, because I think this is the best way that we can learn, we can learn from both sides. Okay, so because we're gonna start with mass spectrometer, and this is just one picture that I want to show before giving you the MCQ question. So here, what you can see is that we have carrier gas, and then we need to regulate that carrier gas, and that's why we do have a regulator. Then we have some sample, the sample that we have extracted in solvent first, and then we have extracted. We already have talked about this, how we can extract, or how we can concentrate it. So so we will have sample, then we will inject sample here, but here we have the carrier gas. So what will happen, this sample will go along with this carrier gas in this column, right? And then based on which one is going first or going to the second place or going to the third place, a detector will detect and will give you the signal. So time to time it will give you the signal, and that's how we try to know what chemical we are talking about, right? So this is something, gas chromatography. This will not give you the name of that chemical, but some gases you can have based on the carbon, nitrogen, or oxygen atoms that we have in that particular chemical. So this is just the gas chromatography, and now I will have some question on gas chromatography. Then we will move to the liquid chromatography. Okay. So the first question is, what is the best way to improve separation between two close peaks? And I have four options here: increase injection volume, change stationary phase, increase flow rate, increase detector gain. As I told you, we have carrier gas and we have sample, and then it will move in a column, right? And which one will be come first? So let's say if there is a some organic, so if it is a glucose, and let's say this is some alkane. So based on the efficiency in the column or with the carrier gas, some chemical will go to the detector at first, and another chemical will go to the second place, and then in the third place, and that's how I will get some signal, right? If there is if these signals are closest to each other, then what is the method how we can improve that separation? Otherwise it will be difficult for us to get to know two different peaks. If I want very clear two peaks, then what should be the method? uh, Increase flow rate will not help us. Why this will not help us? Because we need to we are taking or we are exploiting affinity affinity of our chemical with carrier gas and the stationary phase, right? So if our chemical is more have more affinity with the carrier gas, it means it will go first. If it has more affinity with the stationary phase, then it will go to, let's say, second or at the last place. So, and whenever we are increasing the flow rate, so it is making some interference with the affinity. So increasing flow rate is not it should not be the right option for improving the separation. Yeah, you gave me B option. Yeah, this one is the right, that if we are changing the stationary phase, so we can uh, we can change stationary phase, and based on that, because it will change the affinity, and based on affinity it can separate two peaks. It may increase or reduce the time of one signal with the another signal, so that's why B answer is the right one. Okay. So as I told you, we have a lot of carrier gas that we can use. So which one is giving you the highest efficiency at optimal velocity? And I have four options here: nitrogen, helium, argon, and oxygen. And I gave you one hint that this should be based on Van Dimter curve. Um, Nitrogen is not giving the highest efficiency. There is something else. Nitrogen is little heavier than some other gases. Yeah. So the right answer is helium. So most of the time, whenever we are choosing the carrier gas, this is based on this curve. Van Dimter curve, and you can read about this. And based on this curve, it is said that the highest efficiency, being a carrier gas, is for the helium, because it is inert, it is very light in weight, and that's why it is better to use. Okay. As I told you, in gas chromatography, we have carrier gas, we have sample, and then this sample and carrier gas will uh, go to the columns, and then it will and then within this column we will have that sample, and then we will have some detector, right? So we are talking about here this column part. So we do have different type of column, and one column type is packed column. So you have to tell me the length of that column. If that column is packed column, so we have one column is packed one, and the second is we also have capillary column, right? So right now we are talking about just two, and in the packed column, what will be the length of this column? Typical length. So 30 to 60 meter, 1 to 2 meter, 100 meter, 0.5 meter. So we have a kind of tube, you can say. In that tube, the carrier gas and the sample will go, and then it will it will travel a lot of distance, and then it will go to the detector. And this distance is mandatory actually, because in that column we do have stationary phase also, right? So how our chemical, let's say this is the chemical A, carrier gas is, let's say, B, and stationary phase is C. So how A is interacting with B and how A is interacting with C, based on that interaction, it will decide whether our A will go within 15 minutes to the detector, or within 20 minutes, or within 30 minutes. So that's how we need to know about this packed column. It's very important to know the characteristics of this stationary phase. So what do you think? What should be the length of this packed column? Okay, so if we are talking about the packed column, then typical length of this packed column is 1 to 2 meters. So, and it is important for us because more the length we will have of this packed column, it is better for the detector to detect the signal, right? So, it is mostly 1 to 2 meter. Here you can see the packed column. So in the packed column, so this is just a tube, and so these are the column. Can you see here? These are the column, and if you will go within that column, this column will look like this. And because this is packed, so we already have some molecules that is here, and so this will make the stationary phase. Okay, packed columns generally have, so I have four options here: higher efficiency than capillary. As I told you, we have two type of column, packed and capillary. Lower efficiency, no pressure drop, no stationary phase. What is the advantage or disadvantage of packed column? Does it have higher efficiency than capillary, or it have lower efficiency, or there is a pressure drop, or there is a no stationary phase in packed column? If we are talking about packed column, then I have to see, let's say this is your tube or packed column, and we have here molecules, a lot of molecules that are the part of your stationary phase, right? So whenever your chemical A will come along with some carrier gas, then there is a lot of molecules. That molecules uh, uh, will restrict the movement of this A, and that's how pressure drop will increase. So you can take one example, like if I'm saying that we have a sieve, or you can say filter paper. If that filter paper size is this pore size is large, then your filtering will be easier for you. But if I say that you have filter paper where pore size is very very small, then it means your filtering will be very difficult. And what is the reason that why it is very difficult? Because here pressure drop will increase, because it will be against the gravity will not help your drop to be dropped down. So if I'm taking the example of the packed column, then we have a lot of molecules here that is for the stationary phase, and because of that pressure drop will increase. So if I'm saying that no pressure drop, no, there will be pressure drop. So C should not be the right answer. Yeah, I got A answer. Or we have actually we have a lower efficiency. I will explain why we do have lower efficiency than capillary. Because uh, capillary length is very high, and because of that efficiency will increase for the capillary as comparison to the packed one, right? And here, because there is a high to moderate pressure drop, then it will not help you much. There may be some loss of your contaminant, or you can say the loss of A, because it may not reach to the detector because there is a high pressure drop, and the length is just 1 to 2 meters, right? But if you will talk about the packed column, then yeah, next question is related to packed column, and you will learn how uh, uh, packed column have lower efficiency as comparison to the capillary one. Okay, so we were talking about pressure drop. So pressure drop in packed columns is very low, moderate to high, zero, independent of length. I gave you the example. Whenever we have two type of filter paper, one filter paper have larger pore size, and another filter paper have pore size is very low. So there will be difficult to trickle down the water whenever the pore size is very low. And why this is? Because there will be high pressure drop, right? And it gravity will not help us to percolate that water. So the same case is like the packed column is full of molecules, so it is also making very tight pouring. So pressure drop should be what? Very low, moderate to high, zero, independent of length. Yeah, so pressure drop will be moderate to high, because this is packed one, right? From the name only you can say this is the packed one. uh, your chemical A have to struggle a lot to cross this one to go to the detector, and that's how B answer is the right one, moderate to high. Okay, so we talked about the column, packed column. The second one is the capillary column. So what is the length of the capillary column? 1 to 2 meter, 5 meter, 30 to 60 meter, 100 to 200 meter. If you have any problem with any type of question, or if you are getting any difficulty, you can just write in the chat box any question. 1 to 2 meter. This 1 to 2 meter was the column length for the packed one. Packed column had that typical length was 1 to 2 meter. That actually, this one is defining why capillary have more efficiency than packed one. So let's say this is the packed one and this is your capillary column. And for the packed one, the length was just 1 to 2 meter because the pressure drop is too high, right? And so it will not move. But if we have capillary one, then this is 30 to 60, and this is defining why efficiency is higher as comparison to the packed one, right? I got something. The mass of the clean filter paper used for particulate matter was found to be 10 raised to power 3 mg, I think, loaded with high volume sampler. Yeah, yeah, yeah. Oh, what is the PM concentration? Okay, I have to let me read that again. The mass of the clean filter paper used for particulate matter, measurement after conditioning was found to be this one mg. The filter paper was loaded with high volume sampler and loaded into high volume sampler, and the ambient air sample was processed through the filter. After 8 hours of sampling at 1000 liter per minute, the filter was removed and conditioning again, and the weight was this one. Yeah, actually, this one is very easy. What you just need to see is you need to calculate the volume, right? And after that volume, you need to calculate the concentration because it is for the 8 hours. And this is your flow rate, this 1000 liter per minute. So you have flow rate, that is q, and you have time. So q multiply by t. So q is nothing but you can say meter cube per time, multiply by time, it will give you the volume, right? So so the thing is, if you are having, let's say, 108 mg, so you have to see how much volume we have for this, right? And you know that the concentration is equal to mass by volume. So whenever you are getting any concentration, so this will be 218 divide by volume. And volume, how we will calculate the volume? So we have flow rate will be multiplied with the time, and that's how you will get the volume. So this is how you will get the concentration, right? But you have to again see, you have 8 hours. So here the time here, this is 8 hours, this is in minute, this is in liter right now. Okay. And so yeah, so every time you have to keep in mind the unit and you have to make the conversion. But the crux of how we can solve is that first you have to calculate the volume, how much whenever you are calculating the mass, right? But how much volume you passed through, right? Then based on that you can calculate the concentration, keeping in mind the unit. So this is how you can solve. Is any problem with this question right now? We have to calculate concentration in term of uh, microgram per meter cube. Yeah. Yeah, Lakshmi is giving you some hint. I think you can get that hint from Lakshmi. Anyway, so um, what we were talking about the columns, and we talked about packed column and the capillary column. And this is looking like, so this capillary column is looking like this. So we have this fused silica that will be the part of your stationary phase, and that's how, and can you see how much it is? The length is very high. So just see the length. So it is 30 to 60 meter we can wrap, and that's how the efficiency for this capillary is very high. I think most of the time I skip the numerical question, and the only reason is that you people may not have pen and paper to solve it, and that's why I try to skip this question. But if you want, then yeah, I can solve these questions from next session also. Okay. Uh, okay, so the next question is, capillary column have higher efficiency because larger diameter, no packing material, shorter length, high pressure drop. Okay, you sent me, we want numerical as practice. Yeah, so I will try next week. I will try to put a lot of numerical question in this. So we will try to solve this. Thank you for the feedback. Actually. So we have four options here. Why capillary column have higher efficiency? Uh, Larger diameter, no packing material, shorter length, high pressure drop. What do you think? What should be the right answer? Okay. So yeah, we already have talked about this, packed columns have um, molecules or packing material that we have, and that increase the pressure drop, and that's why the efficiency reduces. But here in the capillary column, we do not have any packing material, and that's why and even the column length is very high, and that's how efficiency increases. Pressure drop increases when column diameter increases, column length increases, pressure increases, carrier gas changes. How can the pressure drop will increase? Yeah, so always pressure drop will always increase whenever we will increase the column length, right? With the, yeah. So just like this, if this column length will be more, then there will be more pressure drop. Okay, so here we were talking about this gas chromatography. We talked about the carrier gas, what kind of gases we can use. Then we talked about this sample, how we can extract it, how we can concentrate it. We talked about the column, two type of column, packed and the capillary one. Now we are focusing on the detector. We do have different type of detector, and each detector have very specific role. And this detector, I can give you some name of the detector. So the one is TCD. This is very common. The most common is actually FID. So we have TCD, FID, ECD, FTD, FPD. We do have a lot of detector, and I think few question is related to this detector only. Which combination gives highest resolution? Short packed column plus high flow rate, long capillary column plus optimized flow rate, short capillaries plus high pressure, very high pressure, packed column plus oxygen. Yeah. So yes, B answer is the right one. Whenever we have long capillary column, and the flow rate should not be very high and should not be very low, so that there is a proper interaction of your sample with the stationary phase. So that's how the flow rate should be optimized. So B answer is the right one. Okay, as I told you, we are going to talk about some detectors, and the first one is FID. So FID primarily detect what? All gas equally, inorganic salt, hydrocarbon, noble gases. Each detector have some detector can detect inorganic salt, some detector can detect the organic things, some detector can detect the heavy metals. So if we are talking about the FID, flame ionization detector, then uh, what kind of uh, what kind of chemical it detects? When we use FID detector, FID detector is mostly used for the hydrocarbons. So whenever let's say, yeah, whenever you have any alkane or even let's say aldehyde, something, but that have CHO, right? uh, then to detect these kind of chemical, we use the detector that is FID. So yeah, C answer is the right one, that is the hydrocarbon. And this FID, because this is flame ionization detector, so what we do is we have a flame, right? And in that flame we have sample. So this sample, let's say we have sample A, this sample A will convert into the ion. So that's why this is flame ionization. So this ion will go, and these ion will go to this that column and then to the detector that is FID. And you know that we can easily burn the organic part, right? And this will be converted into CO2 and C atoms, O atoms, and then ions, and that's how there will be some signal based on that. And that's why whenever we are talking about the hydrocarbon, then FID is the most suitable option that we can have. Why is FID called mass sensitive? It measures molecular weight, response proportional to number of carbon atoms. It detects ion by mass analyzer. It measures pressure. Why we are saying that FID is mass sensitive? Yeah. So you gave me answer C. It detect ion by mass analyzer. No. Why this is obviously it will detect ion by mass analyzer, but this is not the right explanation for the FID being named as mass sensitive. Yeah, so B answer actually is the right one. Obviously, it detect ion by mass analyzer, but why it is known as mass sensitive? Because whenever we will have more carbon atom, then the signal will be more, and based on that only we can detect. Okay, this can be the heavy organic. Organic compound, or this will be the lighter one, so we can have some estimation about our compound, approximate. So why this is mass sensitive is because this is proportional to the number of carbon atoms. So that's why B answer is the right one. FID require which gases? N2 plus CO2, H2 plus air, argon plus oxygen, helium only. we need the flame, right? And how we can get the flame? And then we need to burn our sample, right? So we require some gas for that. So what will be the gas for this flame ionization? Yeah, so I got response B. And yeah, so for FID, what we are using is hydrogen plus air. FID does not detect well alkanes, alcohol, CO2, aromatics. Yeah, C answer is the right one because I already have told that FID is good for the hydrocarbons and it is not good for other inorganic things, right? So CO2 is not the organic thing, and that's why C answer is the right one. FID is considered highly selective, non-selective for organics, only halogen specific, universal. FID is not highly selective. It can't detect much. So let's say if I have alkane, if I have aromatics, or let's say aldehyde, so it is not highly selective. It is not highly sensitive. So it is not highly selective actually. And it is we already have talked about, this is all about hydrocarbon, so it is not halogen specific, and it is not universal because it is just for the hydrocarbon. So the remaining one is the B only, so non selective for organics. Okay, we can call TCD. So this is the another detector that we are talking about. So TCD is called universal. Why? Detect only hydrocarbon, detect only halogens, detect almost all compound, works only with nitrogen. Yeah. So universal means it can detect almost all compound, right? And can you tell me the full form of this TCD? We talked about FID, flame ionization detector. The second detector is TCD. So what is TCD? And I think the first terminology, actually these two terms will define it, why it is a universal in nature. T means thermal, C means conductivity, yes, and D means detector. So each compound have very specific thermal conductivity, right? And based on that, it will give a very different signal. Each chemical will give the different signal, and that signal can be detected by this TCD, and that's why uh, this is universal because we can detect almost all compounds. It is looking like this. So we have carrier gas, we have sample gas, and then we are having the circuit in such a way that each compound with having obviously each compound will have different thermal conductivity, and that's how the response will be different. What is the best carrier gas for TCD sensitivity? Oxygen, nitrogen, helium, carbon dioxide. Yeah. C answer is the right one. And why C is the right answer? Because if we are talking about thermal conductivity, then we should have a very inert gas, right? And which have very specific thermal conductivity, right? So helium is the such gas. So that's why C answer is the right one. Okay, if we are comparing this FID to TCD, then compared to FID, TCD is more sensitive, less sensitive, same sensitivity, selective for carbon. TCD is not more sensitive actually. So actually, this is less sensitive, and also, as I told you, because it can detect all compound, right? It can detect all compound. It means, then why is the need of this FID or different type of detector? It means no doubt it can detect that it is different compound, it is different compound, but what is that compound? And we need more information about this, right? So no doubt TCD is universal, but the sensitivity is less. That's why we use very specific detector also. So TCD have is less sensitive as comparison to FID. Okay, now we have third type of detector, that is electron capture detector, that is highly sensitive to hydrocarbon, water vapor, halogenated compound, and nitrogen. Yeah, so C answer is the right one. Yes, if it is the electron capture detector, then it is good and highly sensitive for halogenated compounds. Because if you know that this is the 17 group, and 17 group easily can give or accept this electron, right? And that's why this is highly sensitive for halogenated compounds. Here you can see whenever we have um, any sample, and if that sample is giving you the electron, that electron will give go to the anode, and that's how this will give you the signal whenever this electron is moving. Why does ECD respond strongly to halogen? They produce flame, they capture electrons, they increase temperature, they reduce pressure. I think this is the simplest question that I prepared. So, because it is related to electron, right? And that's how why this is strongly related to halogen, because they can capture the electron. Uh, ECD is extremely useful for detecting, and we have four options here: methane, pesticide, oxygen, carbon dioxide. Yeah. B answer is the right one. This is pesticide. Can you tell me the one name of the pesticide that is halogenated compound? Okay, so you gave me the example of DDT. Yeah, DDT is the right one. The compound that is halogenated have a lot of chlorine, and this chlorine we can detect using ECT. So whenever we want to see whether that wastewater have pesticide presence or not, then we should go for the detector that is ECT. Okay, so we talked about FID. This is non-selective for the organic. Sensitivity is very high, and this is best for hydrocarbon. We talked about the thermal conductivity detector, that is universal. Sensitivity is moderate, and this is best for all most of all compounds. ECD, that is the electron capture detector, this is again highly selective. Sensitivity is extremely high, and this is best for halogen and pesticide. Then the best one is MS. This is mass spectrometer, because this is highly selective. The sensitivity is very high, and this is best for the identification. And most of the time, we want to know what is that particular chemical or compound. So now on, we will talk about this mass spectrometer. Okay. So, mass spectrometer identify compound based on flame intensity, partition coefficient, mass to charge ratio, pressure drop. Yeah. C answer is the right one, because it identify compound based on mass to charge ratio. Yeah. So C answer is the right one. So here you can see that this is your gas chromatography. So each chemical, one after one, will go to the detector, and here detector is mass spectrometer. And so first we will have this ionization source, and then it will go to the mass detector, and this will give you the signal, and the signals will be nothing but based on mass charge ratio. Okay, so we have two type of mode in GCMS. The one is the scan mode, and another is sim mode. So in scan mode, what do we do? Monitor one ion, monitor selected ion, scan across a mass range, increases sensitivity. We have two mode in GCMC. One is the scan, and another is sim mode. So, for example, you have chemical A, B, C, D, and you have this gas chromatography. And this gas chromatography is giving chemical, first it is giving A, second it is giving B, and then it is giving C. And within each one will be ionized, right? Each one will be converted into ions. And then so for example, if it is the glucose, then there will be CH, or let's say O. So uh, for this A, there will be graph like something, this one. So it may be that this is for C, or this may be for H, or this may be for, let's say, O. And likewise, we will have for the B. And so we will have a very long graph for each compound. So if we are talking about the scan, so this will give you the full graph like this. It will give you each and every peak. So whatever mass we have, so let's say we have very small amount of anything, and the mass of that particular element is also very small, but still it will give you some peak whenever it will encounter some mass and some charge. So either this is large peak, or if it is a small peak, it will give you every peak. So this is nothing but the scan mode. So it is scanning across the mass range. And the opposite to is the sim mode. So in sim mode, we identify some peak, and we just focus on that peak only. And then we have the graph, clear graph of these peaks only, that will come under the sim mode. So yeah, C answer is the right one. So as I told you, we have full scan and we have sim. So sim is nothing but selected ion monitoring. So this will scan wide mass charge ratio, but it will monitor only specific ions, mass by charge values. This have very lower sensitivity. This will have higher sensitivity. It will give you the complete mass spectrum, but it will give you the just selected ion spectrum. It is less effective for low level, but it is highly effective for trace level quantification. And if we want to know the unknowns, then this full scan is valuable for us. But if you know that this can be this particular chemical, and if you want to be just sure about that, then for that targeted compound, then you can go for the sim. And yeah, we have a lot of libraries that is giving you the full spectra, but we have not much library search for this sim part. So if I show you, if this is the mass spectra, so let's say if we are selecting this 11 or let's say 14, and if we are just focusing on this two, then this will be considered as the under sim mode. Okay, sim mode increases sensitivity because it increases pressure, it increases ionization energy, more time is spent measuring selected ions, it increases carrier gas flow. Yeah, so C answer is the right one because in sim mode, we are not focusing on each and every peak, but we are just focusing on some particular ion and some particular peak only. And that's how we are spending more time on selected ions, and that's how the sensitivity of the sim will be increased. Yeah, so I think this is now clear. Which mode is best for detecting unknown compounds? We already have talked about this in the table. So we have four options: SIM, SCAN, TCD, FID. If we want to detect unknown compound, yeah, B answer is the right one. That is SCAN. Which mode gives lowest detection limit? SCAN, SIM, TCD, FID. I think it is difficult for you to compare this four detector right now. So I just gave the answer. So this is SIM. Yeah. So the lowest detection limit is for the SIM. Okay. So we have mass analyzer that is known as quadrupole, and this works as ion source, detector, mass filter, flame. I think from the name only you can give the answer for this. So we have mass analyzer in mass spectrometer, and what is the work of this mass analyzer? So the work of mass analyzer, no, it is not the ion source, but it work as the mass filter. You can search about this. You can learn more about this mass analyzer. So this is present in mass spectrometer, and the work here for this mass analyzer is to filter the mass, and then that will give you mass and charge ratio, right? Okay, so we talked about GC with a lot of detector, and at last GC with MS, that is mass spectrometer. But we are moving to LC, that is the liquid chromatography. And again, in liquid chromatography, we do have different type of detector. For example, Ri, fluorescence, visible, ms. So you have to tell me which detector work on Beer Lambert law. I already have got the response from Priti, that is C. Yeah. So if we are talking about the detector that is ultraviolet visible detector, then yes, this work on Beer Lambert law. And this Beer Lambert law is saying what? It is based on the intensity and absorbance, right? How much we are absorbing the light, or how much there is the decrement in the intensity is proportional to the absorbance by any chemical, and that's how this is giving you the concentration. So this is what is Beer Lambert law. So this is something like this. Again, we do have here mobile phase. So this is liquid, not gas. And then we have here sample. Then this is chromatographic column. We talked about this. And here we will have a different type of detector we may have. And this will give you the chromatograph. Which LC detector is most sensitive? RI, UV, fluorescence, TCD. Okay, I think it may be difficult for you, so I'm just giving you the answer. This is fluorescence. So fluorescence is most sensitive detector that we have in liquid chromatography as comparison to UV and RI. Okay, so we have covered this week 5 content, and now we are moving to the monitoring method. And monitoring method for the air, and in air we have particulate matter, right? So we have a lot of methods and instrument. So mostly we will talk about a lot of instrument, their principle, um, how we can measure particulate matter, not just the number, but diameter, or you can say the size. So can you tell me the instruments that we can use for the particulate matter, to measure the particulate matter? We have a lot. We will talk about, I think, 6, 7, or 8 instrument that we have, and each one have a different principle. So can you give me the name of 2 or 3 instrument that we can use for uh, particulate matter concentration, or you can say number or size? Okay, so Lakshmi gave me one answer, that is high volume sampler. Yes, this is the one instrument by which we can, yeah. So this will give you number and size also. Yes, we can select the size also. Then the second is cyclone. Yes, cyclone is also the right one, right instrument. Any other? Do you know more instrument that we can use to segregate different size particulate matter, or just to know the volume, or the mass or the concentration of particulate matter in the air we have? You rightly said high volume sampler and the cyclone. Can you name one more or two more? Or we have a lot of instruments, we will talk about this. Anyway, so what we will do is we will talk about the particulate okay, Preeti gave me one answer, that is impactor. But if impactor is the part of high volume sampler only, because impactor will help us to segregate different size of particulate matter. So if so we have high impact sampler, and within that we can use different impactors, right? So yeah, impactor is the right, but this is uh, more than an instrument. This is this is the process, or this is the principle by which we can segregate, right? Anyway, so what we will do is we will talk about the particulate matter, how we can measure, what are different principle and how it work. Then we will go to the vapor, how we can, like, what different methods we have by which we can measure the vapor that we have. For example, benzene we have in the air, then how we can measure it, and then measurement of the microorganism. So let's start with the particulate matter. In particulate matter 10 sampling, the classifiers, so the first instrument is classifier, or this is the broad terminology actually. So the classifiers separate particles based on geometric diameter, optical diameter, aerodynamic diameter, and electrical mobility. Yeah. So if we have any classifier, so in classifier we separate particle based on aerodynamic diameter. So can you tell me what's the difference between geometric diameter, optical diameter, aerodynamic diameter? So we have like three type of diameter we are talking here. So what are the differences? Geometric diameter, optical, aerodynamic. Yeah, C answer is the right one. So the first thing that we need to know is, what do you mean by this classifier? The second is, what are the difference between these three type of diameter, right? No doubt C answer is the right one. So let's discuss about these things. So yeah, if we are talking about these classifiers, right? So in that classifier, the one can be cyclone separator, and another one may be high volume sampler. So these two will come under your classifier, because these are helping us to classify the particulate matter, right? So the first thing is, under classifier we may have cyclone based, or we may have high volume sampler, and this high volume sampler is based on impactor, right? The principle is different. For the cyclone we are relying on the centrifugal forces, right? But for the high volume sampler we are relying on impactor. And yeah, let me show you. So we have two type of classifier. The one is impactor based, and second is cyclone based classifier, or you can say the centrifugal based, in which the separation principle for this impactor based is inertial impactor. Whenever you will have more mass of any particulate matter, that will be collected first, right? And taking the advantage of this inertial impaction, we can classify the particulate matter. But here we can use the centrifugal force, and we will talk about these things ahead, but you just need to know about this type of classifiers. We do have a lot of differences between these three in these things. Okay, this is important. What do you mean by this aerodynamic diameter, and how it is different from other type of diameters? So if we have aerodynamic diameter, so this is the diameter of a unit density, and that density is 1 gram per centimeter cube, spherical particle that settle at the same velocity as the particle of interest, right? So this is aerodynamic diameter, and this will account particulate size, shape, and also density. But if we are talking about geometric diameter, so this is just the physical size. It does not account for density and shape, right? If we are talking about the optical one, so this is determined by the light scattering. And this is again is not defining particulate matter 10 regulatory classification. Electrical mobility is different, than we will talk about this also. But the first thing that we learned is we have classifier, impactor based, and cyclone or centrifugal based. Okay. In gravimetric particulate matter measurement, the concentration rho 31 is calculated as mass of air divided by mass of solid, volume of solid divided by volume of air, mass of solid divided by total volume, air volume, and D is number of particle divided by air volume. A particulate matter is the mass. It is not the volume. Particle has the mass. Yeah. So C answer is the right one. Particulate matter. So this is something. Can you tell me the unit for particulate matter? Can you tell me the unit? It is something microgram per meter cube. Yes. So microgram. So this much gram of particulate matter in how much volume of air? So this meter cube is volume of air. So this is something like mass of solid divided by total air volume. So this is the unit of particulate matter. Can you have you heard about this NAAQS? That is National Ambient Air Quality Standard. This is for India. Can you tell me uh, what value of this particulate matter 10 we should have on 24 hours basis? What is the unit for that? And for the yearly also, we have annual. You can say annual. So CPCB, that is the Pollution Control Board, has given a lot of standard how much particulate. So what should be the threshold above which we should not cross that threshold. So uh, what should be the PM concentration, PM10 concentration that we can have in the atmosphere, but if it will go beyond that value, then we can consider that hazardous, right? And we can impose some penalty if someone is increasing that particulate matter um, exceeding one particular value. So can you tell me that value for 24-hour or for annual? And the unit is again this microgram per meter cube. So it is something like, if I'm not wrong, then this annual is 100, and this 100 microgram per meter cube, and this 24-hour, this is 180. You but you need to check. I think I'm sure, 90% sure, but not completely sure about this value, but I think you should know about this value. So what is the safe value that we can have in the atmosphere? But if it is more than that, that will be hazardous for us, right? So CPCB have given one table. You can read about that table. So, and that unit is nothing but microgram per meter cube. This is nothing but mass by mass of solid divided by total air volume. Okay. In an impactor, large particles are collected primarily due to Brownian diffusion, inertial impaction, electrostatic attraction, interception only. Yeah, B answer is the right one, because if we are talking about the larger particle have more mass, it means the inertia will be more, right? If it is a moving in one direction, then it will not change the direction. It will be impacted here only, and that's how it will be deposited. So inertial impaction is very useful for the large particle deposition. And we all already have learned about different mechanism of the deposition. The one is inertial. So because this is the large mass, this will not change the direction. This will go straight to the collector and it will be deposited one. If we have small size particle, then it may be there may be the diffusion, there may be Brownian diffusion, you can say. If we have not not the size is not same as inertial but little smaller than inertial, we have interception. No doubt it is changing the direction along with the air, but still it is impacted, still it is deposited on the collector because it is getting touch with that collector, and that's how this is interception. So we do have different uh, techniques by which we can deposit any particulate matter, and if the size is larger, then we rely on this inertial impaction. Okay, the stopping distance concept in impactor design is directly related to particle color, particle charge, particle momentum, particle humidity. Yeah, you already know about this. If we have more velocity or more mass, so this is nothing but momentum, right? So if we have more momentum, either due to the virtue of this mass or velocity, that will be deposited easily on the collector. Okay, so particle momentum is very important to know about. Particulate matter 2.5 concentration must always be greater than particulate matter 10, equal to particulate matter 10, less than or equal to particulate matter 10, independent of particulate matter 10. Is there any relation between this particulate matter 2.5 and particulate matter 10, or these are independent to each other? Yeah. C answer is the right one because particulate matter 2.5 is the subset of particulate matter 10, right? So either particulate matter 2.5 will be less than particulate matter 10, or it may be equal to particulate matter 10, right? But it can't be larger, or it is not independent because this is the subset of particulate matter 10. So C answer is the right one. Okay, now we are moving to the different separator, or you can say the instrument. This is cyclone. So a cyclone separator remove particle primarily using electrical charging, tangential velocity and centrifugal effects, optical scattering, Brownian motion. So yeah, we already have talked about this. If we do have cyclone separator, then we are dependent on the tangent velocity and centrifugal effect. So I have this figure, so you can say, so whenever we will have any gas, so let's say if gas is coming from here, so it will move circular like this. And what will happen, because every time this is there will be the centrifugal force, right? There will be the centrifugal force means uh, uh, your particle will collide to the wall, right? Whenever it will collide to the wall, then it will be deposited. Okay, and centrifugal force is making the particle to collide to the wall, right? So that's how This is based on the centrifugal force and tangent. Every time it is going tangentially, right? And that's how this is increasing the chances to strike to the wall. So you can see here, if we have small particle, and small particle may experience centrifugal force, and you need to learn that formula, that, and that is very easy to learn, that is mv square upon r. It means if our mass is very small, it means centrifugal force will be very weak, and that's how cyclone will not help us much for small particle to deposit, right? So small particle will escape with the air only, because we do not have high centrifugal force, because the mass is very small. But if our velocity is higher, even and our cyclone diameter is small, then, and so these are the three conditions. If the velocity is very high, cyclone diameter is small, and residence time is longer, in that case small particle can also be deposited. Otherwise it will not, because centrifugal force is directly proportional to the mass, right? So these are the three conditions based on which particulate matter, or the small particle, may also get deposited. There are other method also by which, not just the centrifugal force, but if the size of that your cyclone is very long, then uh, there may be Brownian motion and turbulent diffusion within that. And there may be some, because there are some random motion, and that, because of that random motion, some particle may hit the wall, right? And that's how there may be some deposition, but these are not significant. The significant is just based on the centrifugal force. Okay, next we are moving to high volume particulate matter sampler, typically operate at approximately, so what is the flow rate of the air that is coming to the high volume particulate matter sampler: 16.7 liter per minute, 1000 liter per minute, 1 liter per minute, zero point 0.1 meter cube per minute. Yeah, so B answer is the right one. And that's why this is high volume PM sampler, right? Because there is so if this is your high volume sampler, then it is taking a lot of gas inside it, so that huge amount of particulate matter can be deposited. And how much volume? So this volume you can calculate using, this is your flow rate into time. So what was your flow rate, what for how much time period uh, you had that flow rate. So this will give you the volume of the air. And then it will and you will have the mass on the filter paper in high volume particulate matter sampler. If you have mass, if you have volume, you can easily calculate the concentration. So yeah, B answer is the right one. Now we are moving to another instrument, and that instrument is beta gauge monitor, that also estimate particulate concentration by measuring. We have four options here: mass directly using a balance, electrical resistance, signal attenuation through deposited particles, particle velocity. So till now we talked about cyclone, we talked about high volume sampler based on impactor. The third one is beta gauge monitor. So what happened in the beta gauge monitor, how it estimate particulate matter concentration. So yeah, Lakshmi gave me answer C, that is signal attenuation through deposited particle. And yes, this one is the right one. Let me show you the picture. I think I have one picture. Yeah. So this is something that we have. So this is our beta source. And whenever we have particulate matter, and the detector, whenever it will detect, so the beta source, there will be some attenuation, less intensity, or you can say there will always be some decrement in the energy of this beta source, because if in between that we have the particulate matter, so the concentration of the particulate matter can be assessed by decrement in the beta sources, or you can say the attenuation of the signal due to the deposition of the particle. Okay, so beta attenuation monitor, this is also known as the BAM, and it monitor PM concentration using radiation attenuation. So whenever we will have filter tape, and the particles will be deposited on small spot of the filter, and we will have beta radiation source that can be carbon 14 or krypton 85 that will emit the beta particles. Beta particle will pass through the loaded filter spot, and whenever we you have the clean filter, it means more beta particle will reach to the detector. Whenever you will have the loaded filter, means more particulate matter mass, more attenuation, and fewer beta particles will be detected. And whenever there is the reduction in the signal intensity, that will be proportional to the mass of particulate matter on the filter. So I think that will help you to understand what is the principle of beta attenuation monitor and how it can measure the concentration of particulate matter. Okay, now we have the fourth one. The fourth instrument is optical particle counters. This determine particle size. Just you need to see that beta attenuation, what it was measuring the concentration, right? But here this optical particle counter is measuring the particle size, not the concentration here, right? So optical particle counter determine particle size mainly from gravitational settling velocity, scattering angle and intensity, mass accumulation, chemical composition. Yeah. So B answer is the right one because it is the optical, right? So optical means if we are giving the light from different angle and from different intensity, and there will be some reduction in the intensity also of that particular light, and that angle will give you the size. So yeah, B is the right answer. So this is something like that. We are having the laser. This is our we are sampling our air that have the particulate matter. This is the detector. So this will give you different angle. So we are having a scattering angle, then we have aperture angle, we based on this mirror that we have put here, and that's how there will be some signal, and whatever signal we got, this will give you the particulate matter size. So this is something like that. If you have larger particle, so larger particle will scatter more light. We have, if we have smaller particle, that means that scattering will be less, so scatter less light, and the scattered intensity will be proportional to particle diameter. And that's how we can use this optical sensor to get to know the particle size. Okay. Oh, I already have given you the answer. But yeah, this is another instrument that is aerodynamic particle sizer that determine the size, and this is using the time of flight. So what do you mean? Do you know what is time of flight? So the principle of this aerodynamic particle sizer is based on the time of flight. What is this time of flight? So okay, let me show you. uh I think you can read from here. So yeah, so what we do have is, whenever we have air, and air will have this particle, and what we are doing is we are giving the velocity to the particle. And whenever we are giving the velocity to the particle, and particle is moving in between two laser beam, so different type of particles will have different velocity, and based on that we can tell what will be the size of our particle. So for example, if we have large particle, it means there will be slower acceleration, and slower acceleration means there will be longer time of flight. If we have smaller particle, we have faster acceleration, and we will have short time of flight. And based on this, what we can say is, we can talk about the particle size. So can you see like what different properties we are taking into consideration while either we are measuring the concentration or we are measuring the size? We are exploiting all the properties that we know about the particulate matter, either it is centrifugal property or inertial, or it is uh, time of flight, or it is the optical scattering. So based on different properties, uh, we are designing different instrument to measure it. Okay, so optical particulate matter monitors may not exactly match particulate matter 10 standard because they measure aerodynamic diameter, geometric diameter, scattering diameter, electric diameter. Yeah, C answer is the right one. That is scattering diameter. And uh, retention of particulate matter on impactor depend on particle velocity and geography of the impactor, or momentum and geography. Are you geometry? Are you asking me the question, or you're telling Priti? Okay, so you are asking. Okay, so your question is retention of particulate matter on impactor depend on the particle velocity and geometry of the impactor, or momentum and geometry. What do you think? What should be the right answer? You just tell me and then I will correct it. What do you think? What should be the we already have talked about this, right? Any response from Lakshmi? What should be the right answer for this? Okay, Lakshmi gave me answer both. So do you have do you have option to select multiple selection option? Okay. So for me, obviously the answer both are correct. I agree with the Lakshmi. But more answer. If impactor, if we are talking about the impactor, then uh, no doubt the mass of your particle is very important, right? And again, I told you, along with that mass we also need the velocity. If we have even if we do have higher mass but the velocity is less, then then yeah, it can move along with the air. But if we have the velocity higher, then it have more impact and it will be deposited more. So velocity is important, along with velocity, and velocity is the part of the momentum, right? So because momentum is nothing but it is equal to mass multiplied by velocity. So velocity and momentum both are important for us. And then we have geometry. Then yes, if you know that we need different geometry to segregate different size of the particulate matter. So for example, if you want to segregate 2.5, then your geometry of the impactor may be different. But if you have if you want to segregate, let's say, one the diameter that is 1 micrometer, then your geometry or design will be different. So I think both should be the answer. And if you want to have just one answer, then I will go with momentum and geometry, because particle velocity itself, it is the part of momentum, right? Because momentum is mass by velocity. So I will go with this momentum and geography, uh, because particle velocity is the part of this momentum. Yeah. So I think that's the explanation that I can give you. But if you have both option, then go for the both option. But if you have just one option, then go with momentum and geography. Oh, sorry, not geography. This is geometry. Okay, so what we were talking about, the optical particulate matter monitoring. So scattering diameter is not equivalent to aerodynamic diameter. We have talked about this. Okay, so we have different impactor, and we have single stage impactor and we have cascade impactor. So how cascade impactor is different from single stage impactor? So we have four options: remove only coarse particle, provide size segregated mass fraction, use only cyclonic motion, avoid filter collection. Yeah. So this cascade impactor is not only giving you just one size segregation, but it provide size segregated mass fraction. So we were talking about the geometry, right? So this is something like in cascade impactor we do have different type of geometry that we can use, and based on that we can segregate different size mass fraction. And so I think if you have watched sir's lecture, then it was something that oh, my pen is not working. Okay, so this is something that what is the size, what is the length, what is the design of impactor you are having. Based on that, how it will take so whenever you have any air is moving and it is striking with your impactor, then how your air will move, how it will be diverted. So it is designed on your geometry, right? So in cascade impactors we have different design or different you can say geometry of your impactor. Based on that you can segregate different size mass fraction. Okay, I think this is the simple question. In gravimetric particulate matter analysis, the main limitation of a 4-digit balance is excessive power consumption, limited mass sensitivity, slow response time, optical interference. In gravimetric particulate analysis, so what is the limitation of 4-digit balance? This is something very much related to the detection limit, right? Minimum detection limit, MDL, right? Yeah. So if you have four digit balance, and let's say your particulate matter mass is 0.000056 gram, and let's say if it is just measuring up to 0.0000 gram, then how you will measure that small mass of your particulate matter? So the sensitivity, mass sensitivity, will be limited if we have just four digit balance. Okay. The next technique or instrument that we can use for the particulate matter is differential mobility analyzer, that is known as DMA, that separate particle based on, you have four options: aerodynamic drag only, electrical mobility, optical absorption, gravitational settling. What is the principle of differential mobility analyzer, and how we can segregate particle based on this DMA? Again, different particle, different size particle, or different mass particle uh, will move in a different way, right? In the influence of electrical charges or something like that, electrical field. So yeah, so this is based on electrical mobility. I think I have one picture here. So here what you are seeing is the motion of particle, and motion of particle depends on electrical mobility. So whenever you have smaller particle, even if it has the same charge but will have higher mobility, larger particle will have lower mobility. So it is segregating the particulate matter based on the size. Okay, so this is the another technique or instrument that we can use, that is the DMA. So here also you can read, we are first charging our particles, and then it will move to some chamber that have some electrode, inner and outer, and then in the electric field it will move to some electrode, and the movement will be detected, and based on that we can detect what can be the size of that particulate matter. So in a DMA, particle trajectory depends on voltage and charge, mass and humidity, temperature only, flow rate only. We were talking about electric field, right? Electric field, charging, yeah. And based on that, the particle trajectory will be dependent on, and we talked about electrodes, right? Inner electrode, outer electrode. So whenever we are talking about electrode, then we have to talk about voltage, right? And we talked about we have to charge our particles, then we will make it move from one from one anode or from one electrode to another electrode. So that's how there is a charge also. So particle trajectory will depend on voltage and charge. So yeah, A answer is the right one. Okay, now we are moving to the different technique, and that technique is condensation particle counter, that will enable us to detect the nanoparticle also. And you have four options. So how it detect the nanoparticle? You have four options: reducing particle size, electrically neutralizing particles, growing particle while vapor condensation, measuring gravitational force. Yeah. So right now, because we are right now not interested for particulate matter 10 or particulate matter 2.5, but right now we are more interested to see the nanoparticle or to detect the nanoparticle. And for that we have one instrument, that is condensation particle counter. And from the name itself it is suggesting that we have small particle and we are first aggregating it. So we are growing the particle, and then we are doing the condensation, right? And based on that we are able to detect the nanoparticle. So yeah, C answer is the right one. Okay, another technique or instrument that we have is SMPS system, that combine what? Cyclone plus filter, APS plus beta gauge. We talked about everything, right? APS, DMA, CPC, uh, impactor, gravimetry. We already have talked about these things. Okay, Lakshmi gave me C answer, that is DMA plus CPC. Yeah, you are right. Can you tell me the full form of SMPS? We already have talked about DMA and CPC. But what is SMPS? Okay, let me tell you. So SMPS is scanning mobility particle sizer, and we are combining two things here. DMA, that is the differential mobility analyzer, so that will classify the particle based on electrical mobility. And then we have CPC, that is the condensation particle counter, and that will count the concentration of total number of particles that we have, the nanoparticles, right? So this will help us for the size distribution of ultra fine aerosol particles. And that's how, because this is using two different technique into one, that is the scanning mobility particle sizer. Okay, what is the main advantage of gravimetric particulate matter collection for source apportionment? Real time monitoring, low detection limit for nanoparticle, availability of physical mass for chemical analysis, no need for calibration. Yeah. So C answer is the right one. Why we are still relying on the gravimetry then, even when we have a lot of instrument or technique we already have talked, right? But why we are still relying on this gravimetric particulate matter collection? This is because we need to know from where this chemical or compound is coming from, and for that we need to know the mass of each of the chemical, and we also want to know what is that particular chemical is. So for that we should have that chemical or that compound of to which we are measuring. So yeah, so C is the right answer for that. In cyclone based particulate matter sampling, if we are increasing the residence time, then what will happen? Decrease separation efficiency, enhance particle deposition, reduce tangential velocity, eliminate need for filters. Yeah, B answer is the right one. And why residence time will increase the particle deposition is more, if we have more residence time, it means we do have more chances that particle may collide to the wall, and if it will strike to the wall, then it will be deposited, right? So if we have more residence time, if we have more spiraling or more volume of cyclone, if we have, then we have better chance for the particle deposition. So yeah, you already have seen this kind of instrument. uh, Optical particle counters, so we already have talked about this. OPC and APS both use laser, but they differ because they measure optical diameter versus aerodynamic diameter, electrical mobility versus aerodynamic diameter, mass versus optical diameter, and geometric diameter versus physical diameter. In the optical, it was related to the optical scattering and all. Yeah, so A answer is the right one because in optical particle counter, we are using the optical diameter, but in APS, we were using the aerodynamic diameter. So, no doubt we are using the laser, but the principle is different. So yeah, in APS, that is the aerodynamic particle sizer, we were using the laser beam, but for the time of flight measurement. But for optical particle counter, we were using the scattering. So the principle is very different. The electrical mobility diameter obtained using DMA depend primarily on. Yeah, I think we already have discussed this question. So yeah, this one is, I think we already have discussed. Yeah. When comparing optical aerodynamic and mobility diameter, one must assume equivalence for spherical particle, use standard particle and establish correlation, ignore density differences, use gravimetry as reference. Because we are using different diameter in different instrument. So but at last, how we will measure? Yeah, so what we should do is we should use standard particles, and based on that, we should have optical diameter, we should have aerodynamic diameter, we should have mobility diameter, and we also should need to establish the correlation between this diameter. Then only we can tell in the right way what is the aerodynamic diameter. Okay, now we are moving more to the microorganism thing. So in okay, not right now microorganism thing, but this SEM, that is the scanning electron microscope, imaging of particulate matter. So we can image particulate matter also using some microscope. Image contrast arise mainly from optical reflectance, backscattered electrons, ion emission, thermal radiation. Yeah, B is the right answer because this is scanning electron microscope. Then we are using electrons, backscattered electrons, to tell the proper shape of your particulate matter, right? We can image the particulate matter based on this microscope, that is the scanning electron microscope. Then we have another spectroscopy, that is energy dispersive spectroscopy, that is EDS, identify element based on optical absorption band, characteristic X-ray energies, particle mobility, mass to charge ratio. Yeah. So if we are talking about the energy, so most of the time this is high energy radiation. So this is X-ray energy we are using to identify the elements. You can read about these things later. Yeah, so now we are moving from particulate matter to organic compound. So uh, we do have different again methods by which we can estimate the concentration of organic compounds and ions. So now we are moving little bit to the organic compound concentration measurement. So for organic compound analysis from PM filters, extraction is typically done using dilute nitric acid, deionized water, organic solvent, hydrofluoric acid. So if it is an organic compound, then for this extraction, what we need? Organic like organic, right? Inorganic likes inorganic. So if you want to extract, then for this extraction, what we need? Not B, not D. It is, as I told you, for the extraction, if we already have talked about it, if we want to extract organic compound, then we need the organic solvent only. The one example is hexane, right? So for organic compound, for the extraction, we need the organic solvent only. Yeah. So C answer should be the right one. Okay, because we have moved from particulate matter to now to the organic part. So we have elemental carbon. If we have elemental carbon in particulate matter, this is commonly referred to as. We have carbon, but this is in the form of particulate matter. Uh, please talk about purge and trap. I think next I think after 5 or 6 question, I will talk about this purge and trap. So this purge and trap, but I give you the brief description of this purge and trap. So this is something that we are giving the excess of nitrogen. We are giving the excess of nitrogen so that we can. So this is something about the vapor. So for example, if we have benzene in the air, right? We have benzene in the air, and then what we are doing, uh, either we are extracting that benzene in the solvent, in the liquid, right? If we are extracting in the liquid, then if we are moving that liquid, the liquid will have the benzene, and if we are moving it to the instrument, let's say gas chromatography only, so what we have to do is uh, we have to remove this benzene from the solvent. Okay, so the one method to remove this benzene from the solvent so that this benzene can go directly to, let's say, gas chromatography, the one method is purge and trap. So this is something that we will purge this solvent with some gas. So for example, for with the nitrogen, if we are moving a lot of nitrogen in the solvent, so what will happen? So our volatile, let's say benzene, will move and will vapor. Okay, and then what we are doing? We are doing the condensation. So after condensation, then so this is the one method how we can extract our vapor, for example benzene, from the solvent. So this is about the purge, and I think I have a few questions related to purge and trap in, like, after this 4 or 5 question. Anyway, so Lakshmi gave me C answer, that is soot. Yeah. So whenever we have elemental carbon in particulate matter, that will be referred as the soot. uh the one is silicon is also the carbon thing, right? Silicon is difficult to measure using nitric acid extraction because it form volatile compound, it require hydrofluoric acid for dissolution, it oxidize rapidly, it interfere with iron chromatography. What should be the answer for this? 143. Let me show. Yeah. Okay, so I got answer C. Not C is not the right answer. Because this silicon is difficult to measure using nitric acid extraction, and that's why we need hydrofluoric acid for dissolution. This is the right answer, but I'm right now moving to, if you give me the permission, then yeah, there is a lot of question, but I will, because we need to consider a lot of things, but because you were talking about that purging, I'm just showing you some. Mm, we need to talk a lot about this thermal desorption, and yeah. So there is the one question about this purge. In purge and trap analysis of VOC in water, the purge step primarily, this will strip volatile analyte into gas phase. And here you can see, so you have sample is in the liquid, so you are purging the gas. So for example, if it is the argon or helium, or most of the time it is the nitrogen, if you are putting that nitrogen, then what will happen, your sample, let's say benzene, will go to this another tube, and here you will have the water condenser, then you will have the thermal desorption unit, and then it will go directly to the GCMC, right? So this is something about the purging. So purging is that you are putting a lot of gas so that vapor your vapor in the water can go out to the first to the thermal desorption unit, and then to the GC and MC. So yeah, I think one more question. In purge and trap system, the trapping step occur after gas phase stripping. So yeah, so I try most of the time that we need to cover like each and every topic. So we still have some topic that we need to cover, that is desorption unit. Then we need to cover breakthrough curves. So I think the time is up, so we will solve this type of question in next week. And yeah, in next week, as you suggested, I will come up with a lot of numerical question also, so that we can solve that too. And yeah, if there is any another suggestion, you can just let me know. Otherwise, I think this is the time that we should leave. Thank you, Priti.